thing here. Okay? This is a simple current mirror. I can put ground, can put minus C. Yeah? So this is a simple current mirror. This current IC2, if this Q2, Q1, this will mirror to here. So I can change the emitter area ratio to get different amount of current mirror over. So as long as I design this well, this current is approximately equal to this, then this will mirror to here based on the emitter area ratio. So far so good. So then, that means this point, theoretically, if this is a good current source, this point, the voltage I put anywhere doesn't matter, okay? Because the current will be relatively constant given by this. So far so good. So because why this guy, I already unconditionally bias this guy in forward active region. Theoretically, depend on the BBE here, 0.7, 0.6 something or whatever. I have a curve here and I'm biasing somewhere here. So then it's determined by this guy. This guy is the AC variation of the any variation here over is the dynamic resistance, which is your RO. If you look at the voltage here, RO, AC resistance. Okay. So if you look into here, from here to here, you change this guy to ground, AC resistance. You see here to here is a just RO. I just want to show you to make it easy for you. You notice this guy is a diode, So if it's a diode, then later I will show you for the MOSFET. This is more or less close to 1 over 3 or your emitter resistance in your lab to see RE. So then this guy base is here. Then you have your R pi. Then at the output there you have the dependent current source, right? Your R, right? Then you want to measure the resistance here, you switch off the signal anyway, there's no current, you switch off, there's no current flow. Then this guy is open circuit, you see only R out. That's why this guy is only R out, right? Got it? So if this is only R out, then R out can be very big, but if I want to make this guy as a system, this point to this point, here the voltage variation, the current variation with respect to the voltage is less sensitive. I want an even better AC resistance. How could I do it? Think about it. When you do your common emitter amplifier, there's one very difficult case I showed you before. If I put an emitter resistor there, the output resistance will raise by 1 plus 3 and something, right? Yes, precisely. If you put the output resistance there, put something there, then you find that the resistance, you work it out, will be R out 1 plus Gn, approximately this guy. But it could be this guy parallel with R pi something. So that means I raise it by this factor. Make it several times of R. So can I do it that way to improve this current sensitivity to voltage change to be less sensitive? So yes, by increasing this R out, the output AC output is the current, then I put the resistor. And this one is called the Wheeler current mirror. Got it? And then you notice it, this structure and this structure is the same. There is this resistor there. Okay? So of course the other side is basically another current mirror. Okay? So you can see this is diode connection. Mirror this guy. So can I take this away? I'm going to go to solve this problem first. Okay? So let's look at this problem, what it says. It says that AE3, okay, area of emitter AE3 equal to 10 times AE4. Okay? So can I just recall, have you recall, the collector current of the transistor, you take into account the emitter area, saturation current exponential, VBE over VT, then 1 plus VCE over VA, right? So if we ignore, see what the question says, assume that infinite current gain. Infinite current gain means beta equal infinity. When beta equal infinity, remember, base current equal to collector current over beta, right? If beta infinity means base current equals 0, right? So that means there's no base current, huh? We assume base current equals 0. So this is because beta equal to infinity, huh? That's the question here. Then secondly, ignore early effect means that VA is equal to infinity, huh? So then your IC essentially is equal to IE, IS exponential VBE over VT because I ignore early effect based on the question. So then if that's the case, ask yourself, this guy is base, this guy is emitter, huh, for the PMOS. Do they have the same base emitter voltage? Base connect to base, emitter connect to emitter. So if you look back to this equation, this is the same. This thermal voltage, if they are at the same temperature, is the same. IS saturation current, if they are fabricated on the same size, they are the same. So the only thing that is different is emitter area, right? So if I say IE3 is 10 times IE4, that means IC3 will be 10 times IC4. So that means this guy means that IC3 is equal to 10 times IC4. So where's IC3? This current. Where's IC4? This current. Correct? Another thing I want to tell you is that this is IC, this is MPN, IC1, and this guy is IC2, right? So, since there's no base current, isn't these two currents the same? So, I must tell you that IC1 is equal to IC3, huh? Correct? Second thing is IC2 must be equal to IC4 as well, huh? Since there's no base current. This one clear? So what the question gives you the second thing? AE2 equal to 10 times AE1. AE2 equal to 10 times AE1. So now can I ask you, does it mean that IC2 is 10 times IC1? Yes or no?
Yes.
If you think yes, don't you see there's a contradiction now? This guy is 10 times this guy. Then if you say the area here 10 times this guy is 10 times this guy, then it's contradicting, right? So what goes wrong in the second part? Under what condition I say this guy is 10 times this? Not just because of this, but also because the VBE is the same, right? Are you sure this guy, the VBE is the same? This VBE, this VBE. This guy VBE is equal to this plus this, no? So the VBE is not the same. How can the IC be the same? You look at this equation, although these are the same, but the VBE is different means these two will have to be different. So there's no contradiction. It's just that I cannot say, because of this, then this is 10 times this. Only when the VBE is the same. And this is the key point of solving this problem. Okay, so the key point I will tell you, this is VBE1, this is VBE2, right? Correct? Can I express the voltage across the resistor? Let me call this voltage VR. This is equal to this plus this, right? So this must be equal to this minus this, right? Okay, so that means my VR is equal to VBE1 minus VBE2. Correct? So from this equation, can I express my VBE in terms of IC? Here, if I express VBE in terms of IC, it's basically, okay, I'm taking
No, I told you because I was listening to him. And then I said
VT logarithmic
I didn't guess.
IC over IS, huh? Okay, this IS, oh sorry, Okay, IS means this whole thing.
No, because it's
So when I say this is 10 times this, basically it's the same as saying that my
can you
IS2 is 10 times IS1. Your IS4 is the same. Okay? So if I want to simplify it, round it together, I use IS. Is it okay? So if it's okay, then now can you express VBE in terms of thermal voltage log IC1, because I'm VBE1 means IC1 over IS1. Minus away VT log IC2 over IS2. Is it okay? If this is okay, can I pull out the VT? And then this minus this, right? Log A minus log B is log A divided by log B, am I right? So then I will have log IC1 IS1 divided by IC2 over IS2. Alright? So this will give me VT log IC1 over, if I put this guy IS1 times IS2 over IC2. Alright? So, what is the ratio of IC1 over IC2? It's the same, these two. So this ratio, okay, IC2 over IC1 is the same as IC4 over IC3, right? 10 times, right? So then this will be equal to VT log 10 times. Okay? Then IS2 over IS1 is also 10 times. So VT, what is it? KT over Q, right? And then if you take it as room temperature, then it's 25 milli, right? Times log 100, right? So you can work it out what it is. You will get the voltage across this resistor. So if you can get the voltage across this resistor, can you get the emitter current? Okay, just divide by resistor value, you get the emitter current. If you get the emitter current, can you get this collector current? Since data is infinity, it means these two are exactly the same, right? So then your collector current also gets. So the question asks you to calculate IC2, you calculate based on this. Okay, I want to take this opportunity to show you a solution. At the same time, I'm going to tell you why this circuit is important solid state circuit electronics, because we can use for thermal sensing. Okay, and then if we can use for thermal sensing, then today all your CPU, all this very smart, they can put a lot of this transistor, resistor them to sense the temperature so that they can find whether there's a hot spot, and then they cool down, shut down this part and part and so on. Okay. Otherwise, you cannot put it into solid state circuit, you cannot put it into IC, then you cannot sense temperature on IC directly. It's difficult for you to do all this kind of thermal management. Okay, so let's look at the solution. So let me show you. This is a solution here.
Then my hand is very, very rusty.
Okay, I do it. The circuit I already showed here. I just showed the solution here. It's very similar to what I did here. So basically, the key point is because these two phase emitter voltage is the same, so that causes the current, and here depends on the emitter area ratio. So if this emitter area is 10 times this, then this will be 10 times this. But not for this case here, because the two VBE are not the same, because there's a resistor there. So that's why there's no contradiction just now, otherwise there will be a contradiction. So even though the area is opposite ratio, it doesn't cause a contradiction. So all you need to do then, you solve by the voltage difference is actually this voltage across IC and IS, which is the logarithmic form here. Okay, once you get that, you simplify, then you know the current ratio of these two, and you also know the IS ratio of these two because it's given by the emitter ratio. Okay, so then you're able to work out what is the voltage across this resistor. So once you're able to work out the voltage across this resistor, you can find the current through this resistor. Let's take this voltage divided by this resistor. So once you get this emitter current will be approximately equal to this in your beta is not infinite. Okay, if your beta is infinite, then they are more or less exactly equal because there's no base current. So this is the case here. So the IC 2 is equal to IE2. So you can calculate IC2. Okay, now once you get this, I want to get to the point why this guy is also called this voltage here. This voltage here has a special name called proportional to absolute temperature. P proportional to absolute temperature. Why? Because you notice this expression. This guy is constant. This guy 25 minutes before I still room temperature. If I want to get it correct, Pt is equal to kT over Q, right? Then log 100, right? So this guy K is a Boltzmann constant, it's a fixed constant. Q is the electronic charge, it's a fixed constant. This guy is also constant, right? And this is absolute temperature. So you can see then it becomes, this voltage is linearly proportional to the absolute temperature. So it's called proportional to absolute temperature. So what is good about linearly proportional? Meaning that I have this guy increased by that amount, that guy increased by amount with a fraction. So in this case, as long as I can test it, okay, what is the resistance value for 0 volt at 0 degree? What is the voltage for 0 degree? Then by looking at the voltage, I know what's the temperature, having a temperature, because it's proportional temperature. Isn't that thermal sensing? You convert temperature to voltage, then you can have what is the temperature. Okay, so that's why because of this circuit today is very useful. Okay, even on the silicon. So can I clear this question? We done it actually. Okay, that's why the question is answered. Can I clear this? So we can now look at the next question. Oh, good. So next question is the last question for this tutorial, right? So I'm catching up quite fast, okay? So I'm going to show you something. Here I take a little bit of time to share with you what is the transfer function. So now we are moving from current mirror to a system, okay? That is consists of the real world system. So basically, let me see if I have some slide to show. Okay, this is called the transfer function, and this is S is the Laplace transform. Okay, so basically this transfer function S here is actually J omega. Omega is the frequency. Okay, so this and Ts can be current gain, voltage gain, whatever. It's just a transfer function. Transfer function is something over something. Got it? Okay. So because your real world system is not just resistor, so if it's just resistor, you know what happens. Let me make things easy for you. If you have a resistor, I apply a signal. What will happen to the voltage current here? It's simply that resistor related to resistor, the current will be the voltage divided by R, right? And this is sine wave, this sine wave, that's everything real. No phase. Okay, the current, that means if the current like that, the voltage like that, the current will also be same phase, no change in, no shift in all these things. But if I put in a capacitor, not so simple, right? Because the current become integration of the voltage with respect to time. If this guy is time changing, if this guy is not time changing, if this guy changing in time, what is the current here? Okay, if 1C dt, right? It become integration. So you start the integration, okay, then it really depends on this signal. You can change the signal shape and all these things. Then there may be a phase shift and all those things, right? So let me help you to understand why now you move from a real to a complex number. It's because, let me ask you, if everything same reference, okay, no issue. But if this guy, same amplitude, same frequency, like that, how you express this? If this is A sine omega t, then this is A sine omega t plus some phase, right? If you agree with me, this is amplitude, this is phase, right? Then I can write something as an amplitude with a phase, right? Correct? I mean, I can express this what amplitude is Z, phase angle, right? And notice, what is this? This is the polar form of a complex number. You can change it to a rectangular form, which consists of the real part and imaginary part, right? Okay? The real part typically, if this is an electronic system, the real part is constituted mainly by resistor, which doesn't depend on frequency. It doesn't change the waveform and the different frequency pass through. It doesn't change the shape, doesn't change anything, right? But it is capacitor inductor, you can change. You can even move the phase. Then it becomes complex number. That's the reason why this guy, you typically express this in the impedance of this guy as a complex number. Because of this, you can introduce phase shift, introduce all these things. Then it becomes things like that, right? Then you have this kind of things in the system. Okay? So I just trying to make the abstract mathematics more realistic to you. Otherwise, you learn mathematics, complex number, you don't know where complex number come from. It do come from things like that. Basically, you can actually observe things change because, and then it becomes a magnitude phase form. Then the magnitude phase actually is a complex number, essentially. So then, if that's the case, then if I can express, I still want to keep the same relationship of Ohm's law. That means voltage current still have that relationship, then I have to introduce the impedance instead of resistance. Real resistance just real, and then impedance then can consist of both real and imaginary. Make sense now? So if I have two resistors, R1, R2 in series, then this will be R1 plus R2, still real. But if I have one resistor, one capacitor, then I will have R1 minus J1 over omega C. Now I make this as a complex number. Then I can change this to a polar form. Then I can apply my own law to find the voltage using Laplace transform. Okay? So then if I can do that, I can create this kind of transfer function for voltage current gain. I get the general big concept for you. I'm going to show you a simple equation why the transfer function comes first. Then we do this question. Is it okay? And then is some extra slide. Hopefully it doesn't take me long. I need to get to the subject one. Where's my yes,
Wow, it's manipulate lah, make it simple. It's about finding the poles and zeros. The one that we learn in C, check the set. The one that we never use the dimension. So when the numbers are poles and zeros, they are come with come on, man. Yeah,
Okay, I don't want to introduce something too complicated. I just want to tell you, okay. Can I clear this first? This is not completely electronic. This actually more signal and system, okay? But then they are linked, okay? They are linked, knowledge actually linked. So what I want to highlight to you is that you can see that in real world, there's a lot of system. I actually don't know what is inside there, but I can characterize this system as long as it is a linear time invariant system. And this kind of system happens almost everywhere. What do you mean by linear time invariant? It means that the characteristic of this system doesn't change with time. Okay? So it's time invariant. If it keeps changing with time, very difficult to characterize. Linear means that you can apply superposition. It's not the relationship is not square and all those things. That is not linear. Okay, so that is easy to do superposition. Then the next thing is, but we allow this system to be complex. Meaning they can have resistor, capacitor, inductor, everything put together. So then you apply a signal, then you have this phase shift, you have all this integration, differentiation appear like what I just now tell you. So this is very real system. So how do we typically characterize this system? We can characterize by injecting an impulse. Impulse means if you are able, of course, it's very difficult for you to do exact impulse, but assuming you can make the only one, this is an impulse. Okay, so you can make an impulse there, and then apply the input to this system. You measure the result. Okay, you can time varying thing. Although you should one impulse, but you can have, based on the system, you can have quite complicated response. So that is called the impulse response. And the impulse response, I call it HT, for whatever linear system there. Okay? So then, once you know this HT of this guy, now you apply any signal, I can tell you what's the output. Because any output, any input you apply XT, is basically you do a convolution and then you take the input, then multiply, shift it across time. You get the response, that response is your output from an unknown input. Now, so that means, if that's the case, means I can just characterize the system, even though I don't know what is built off, by an impulse response. So then, what Laplace transform do is to, impulse response, your convolution is actually something that is difficult to do. So Laplace say, I can actually change everything in this system, okay, convert it into a Laplace transform equivalent, the input convert to a Laplace transform equivalent, then I can predict the output, okay, by taking the transfer function, Hs, okay, which is just how you see, the S appear, S is because you convert the time into the Laplace domain. Okay, so then you have Hs. So then this time you don't need to do convolution, just do multiplication. Okay, so I'm going to show you a case why this works. Okay, I don't want to go through mathematics that leave it to you. You notice that for a linear time invariant system, assuming that you have the L, a constant, differentiate n time, n order, in Laplace transform is the same as you take this S, S is j omega, raised to the power n time, then L single derivative. Okay? So now this is quite common, you see, the capacitor current in time domain is C differentiate dV by dt. So if you apply Laplace transform, okay, of the impedance of a capacitor, is actually the voltage across the capacitor in time domain divided by the current through the capacitor in time domain, right? Then you apply the Laplace transform. What will happen? Then you take the Laplace transform of the voltage, you take the Laplace transform of I is equal to this, right? So now you can see this guy I can change it to SC, and then dV by dV become Laplace transform of dt. So these two cancel, I got 1 over SC. That's the reason why your capacitor, impedance of the capacitor after Laplace transform is 1 over SC. Okay? And S, if you substitute as j omega, so now the j below, right, you multiply both sides, numerator, denominator by j, you end up with minus j. Okay, that is ZC. So for the same reason, I can do with inductor. Inductor voltage is L di by dt, right? Then the impedance is voltage over current for the time domain waveform. You apply the Laplace transform of this, then the voltage I convert to this guy, and apply the Laplace transform, I get SL. Then Laplace transform of the current. Bottom is also Laplace transform of current. These two cancel out, so you get SL. So that's the reason why the impedance of the inductor is SL. And S will be replaced by j omega. This is what. Then you have the complex number now. Okay, so I just want to show you with the Laplace transform. Now, forget about this one. This one is I'm trying to show in time domain when I solve it, I also get the same equation. So if I'm interested in the Laplace transform of this voltage, I'm interested in the this is the input. So the voltage gain or the transfer function, voltage transfer function will be this over this, right? So if I do Laplace transform, then I need to change this guy's capacitor to 1 over SC, right? So then this voltage here, voltage divider rule will tell you is equal to 1 over SC, this impedance over the total impedance is R plus 1 over SC, right? So then you simplify, you get 1 over SRC plus 1. So substitute S by minus 1 over RC, or this one I'm going to tell you this is pole. So let's look at, if you substitute X by j omega, then you get this transfer function, okay? And this transfer function, you can see that if I replace, okay, 1 over RC as omega p, then 1 over RC is what we call the time constant, and that has something to do with your cutoff frequency for the first order equation. Why first order? Because there's only one pole, okay? There's only one simple one, okay? There's no square poles and so on. So you can see for this, I can actually change it from the complex number into phase magnitude. If exactly your frequency is equal to this pole, you notice that it's exactly 3 dB. The voltage is 0.707. That explains why I say this is related to your cutoff frequency, the drop of voltage. So I think this part, don't worry, it's not part of Eleanor economy. I just trying to tell you that just now you saw the transfer function, numerator, denominator have all this S, all this is coming from, you apply Laplace transform to the system, a real world system. With all the components, you change it, resistor, keep it, real R, capacitor change to 1 over SC, inductor change to SL. Then you do the standard way, you do your impedance, all this. But now everything is in the Laplace domain. You'll get the transfer function in the form of Laplace with the S there. And S is equal to j omega. That's all. Okay, can I clear this? Okay, after I clear this, I want you to understand two things. I also want to, this one is to explain instability, why the pole must be whatever. So what I want to highlight one simple thing is, this is the transfer function, one of the typical transfer function. So, in fact, if I don't do Laplace transform, I can still solve things using differentiation integration, right? So if you do differentiation integration, eventually you end up with differential equation. So the differential equation of this guy and the Laplace transform of this guy have a relationship. These two exactly the same. I don't want to show you too much about how I can convert a differential equation directly to Laplace transfer function. So there are two equivalent, but what is important, I want to use this to tell you what is the meaning of pole and zero, because you learn pole and zero, right? So if I have a transfer function, Hs, okay, it can be a voltage transfer function, current transfer function, basically output over input. Then if I take into account, I can always express into something A S plus B, depend then below also can have S plus, or maybe I put 0, Z1, Z2, this is P1, S plus P2, all this. So if I can make the transfer function appear like that, can you tell me the magnitude of this guy will it go to 0 when any of these factors go to 0? If I make S plus Z1 0, that means my S must be equal to minus Z1. If this happens, this guy, no matter what frequency it is 0. Got it? So that's why this is called 0 of this transfer function. So can you determine other 0 of this transfer function? This guy, right? S equal to minus Z2 is also the 0 of this transfer function. So I'm showing you the exact transfer function for this guy here, how it looks like. This is the point. This is a point. It can be complex number. Then we change it to phase magnitude for the 0. So when your S is equal to this, the magnitude become of the transfer function becomes 0. That's why it is called 0. So the I explain why 0. So 0 appear in the numerator. You can determine 0 from the numerator. And 0, since S is related to frequency, basically you find at what frequency the transfer function is equal to 0. The transfer function magnitude can be 0 at certain frequency. So this is what you find. So another thing, what is pole? Okay, it's not so complicated to understand pole. It's really like your literal pole. When you see a pole very tall, right? It's that pole. So why is it called pole? Because imagine if this thing goes 0, any of these factors goes 0. This guy goes infinity. Infinity very high, it's like a pole. But in real world system, you can never go all the way to infinity, so you'll chop at somewhere saturation. So you can see where are the frequency point where you have the pole. And it comes from all this. Okay? So now if I show you this, can you tell me where are the 0, 0 is at minus 1, minus 2. The pole is at the other transfer function on this 3 cross here. Minus 3 is 1, minus 1 plus j, and minus 1 minus j. You can see that the poles always occur in conjugate form. If it's not real, if it's real, then you will just real 1. If it's imaginary, then you always have 2 in conjugate form. That's what I'm trying to say. Okay? So for your case here, I doubt you have conjugate pole given to you. For your case, you always give real pole. So then you can actually find out the signal frequency that will give you exactly the very high gain. Okay? So now let me show you how to solve this question. Okay? I think I need to go back to the original question. Then we can complete this one today. So this is the transfer function. Ps equals to 10 to the power 12 S squared S plus 10 S plus